Here are some important points about acetal and hemiacetal formation. A lot of these were mentioned, so we're summarizing them here. Hemiacetals cannot be converted to acetals with base. We already established that when we discussed base catalyzed addition of alcohol. So you have to use acid catalysis to form a full acetal, an acetal. Hemiacetals are difficult to isolate, as we mentioned, unless it's part of a 5 or 6 membered ring. You will see those when we get to the carbohydrate chapter. The same factors, this is very important, that govern equilibrium in hydrate formation also govern the equilibrium in hemiacetal and acetal formation. So we talked about the electron withdrawing groups, talked about electron donating groups, etc., and sterics, all of those, whatever applied to the addition of water to form a hydrate, still apply here. So once again, the more stable the carbonyl, the less favorable the addition. Addition is favored for formaldehyde and aldehydes with electron withdrawing groups. So this is a summary. So if an acetal is placed in excess water with a trace of acid, the ketone will be recovered from the reaction mixture. This is known as hydrolysis reaction. So hydrolysis reactions are very, very important in biochemistry. In fact, acetals and hemiacetals will be seen in carbohydrates. You will see them. So here's an acetal. If you react this, the trace amount of acid and water, you can go back to the ketone. So that's hydrolysis. There's a mechanism for this. It's really, really the reverse, the exact reverse of the acetal formation. So now you're going back to the ketone. So imagine it's playing in reverse. Since acetals can be hydrolyzed under mild conditions to regenerate the original carbonyl compound, they are often used as protecting groups for aldehydes and ketones. So these are excellent to use them for protecting groups. So if you would like to protect the ketone because it's available, or the aldehyde, it's available in addition to other carbonyls that may react, also react, so you can actually protect them. Because remember, aldehydes and ketones are more reactive than esters and carboxylic acids, amides, etc. So again, they can be used protecting groups only. Okay, so this is only for aldehydes and ketones. You can't use hemiacetals, acetals for, let's say, acid chlorides. Can't do that. Only for aldehydes and ketones. Cyclic acetals made by reacting carbonyls with diols are the most commonly used protecting groups. Cyclic acetals are formed much more readily than acyclic acetals. So we just talked about cyclic acetals, and this is the product of a cyclic acetal. Sorry, acyclic. So this is acyclic. But cyclic are interesting looking. They look like an alien. All right, so let me actually redraw this because it truly is it's making me draw it like an alien. So here it is. So it looks like this, and I'm going to show you how this forms. Okay. So I'm going to number one. I'm going to number this as 1 and 2. So here's 1 and 2. And if you notice, what's happening is each oxygen. So this is basically an OR. And this also is an OR. But it's cyclic. It is cyclic. And usually what we use for this is we use glycols. So those are glycols, meaning, you know, this is the most common one. So you have alcohol groups on both ends. And again, they would form this acyclic, the cyclic acetal. So this is called a cyclic acetal. And again, this one is more favored than the acyclic. Very well. So let's talk about the addition of hydrocyanic acid, or basically adding CN minus. And it's a very simple mechanism compared to what we did. So cyanide ion, CN minus, adds to the carbonyl group of an aldehyde or ketone to form a tetrahedral intermediate called cyanohydrin. We did actually see those before. The way we say hydrogen, we saw something called halohydrin or halohydrin. So now it's a cyanohydrin. So meaning you have an OH on attached to the same carbon that the cyanide is attached to. So here is the mechanism. NaCN minus, meaning you have CN as a nucleophile. Attacks the carbonyl carbon. So we say this is a strong nucleophile. Very well. So let's continue. And of course, you know what would happen next is a protonation. So we have the acid. Here it is. Just like that. And again, this is called a cyanohydrin. Now, we should just, before we get to the important points, if this is ever written as HCN, you should be able to understand that that's the same thing as these reagents. So if I have NaCN, that means I have Na plus NCN minus. Now, if I have HCN, and of course, and if I have H3O plus, it means you have the acidic hydronium here. So this is what is meant by HCN. This is the same as HCN. So if you ever see HCN written here, that's the same as these two steps of reagents. A few important points. This is a new CC bond forming strategy. Here's a new CC bond formed. Let me put red right here. For aldehydes, and most aliphatic ketones, the position of equilibrium favors cyanohydrin formation. So this is favored. For many aryl ketones and sterically hindered aliphatic ketones, the position of the equilibrium favors the starting material. So once again, if you actually have sterically hindered ketones, like you have a bunch of groups here, methyls, even if you have two methyls or even have ethyls on each side, or if you have a benzene ring attached, then again, this will not be as readily of a reaction as it should be. So again, the reason why this reaction is favored is because aldehyde is not as stable as a ketone or a sterically hindered ketone.